Let's talk about vector operators in quantum mechanics. So in classical mechanics, we know that vector v is any quantity which has d components if we are living in d-dimensional space, and the components vi, they transform as summation over j, rij, vj, where rij are the matrix elements for rotation. But how do we know, how do we characterize vectors in quantum mechanics? Or more precisely, how do we characterize vector operators in quantum mechanics? So in quantum mechanics, I know that any ket alpha under rotation, under some rotation operator, transforms a dr acting on alpha. Now suppose v is a vector operator in quantum mechanics. So what I assert that, this is the assertion, that the expectation value of the individual components should not change under rotation. That basically means this quantity should be equal to alpha d dagger vi d alpha, which is nothing but summation over j rij acting on alpha vj alpha, because these are the numbers which I can take outside. So I basically assert that this quantity should be equal to this quantity here. But this is valid for any arbitrary ket. So that basically implies that I should have d dagger rotation acting on vi dr should be equal to summation over j rij vj. So this will be the defining condition for my vector operator, and let us find out what it entails. So this is my defining condition. Defining condition. Okay. So let us talk about an infinitesimal rotation element dr given as 1 minus I epsilon j dot n cap by h1, where j is the angular momentum operator. Now clearly d dagger r will be 1 plus I epsilon j dot n cap by h1, and my assertion was that d dagger vi d should be equal to summation over j rij vj. Okay, so that will basically imply that 1 plus I epsilon j dot n cap by h var vi 1 minus I epsilon j dot n cap by h var, that will be equal to summation over j rij along some rotation direction n cap through rotation angle epsilon acting on vj. But this is basically vi plus I epsilon j dot n cap by h var vi, this thing multiplied with 1 minus I epsilon j dot n cap by h var equal to summation over j rij vj. Okay, but that thing is equal to vi plus I epsilon j dot n cap h bar vi epsilon j dot n cap by h bar vi minus, or I into minus I will become plus I, plus 1 I epsilon 0 dot n cap. Okay, and then there will be this thing will multiply with this one, so minus I epsilon vi into j dot n cap by h bar plus order epsilon square term, and that should be equal to summation over j rij vj. Now I will take terms which are up to order epsilon. That will basically entail that this thing is almost 0. So I will have vi plus I epsilon by h bar j dot n cap commutation with vi, that should be equal to summation over j rij vj. Or I can take the I down and that will basically invert my commutation. So basically I will get vi plus epsilon. I will take this I here in the denominator and this will flip, like swap itself. So I will get vi plus epsilon by I h bar vi j dot n cap, and that should be equal to summation over j rij vj. Okay, so for infinitesimal rotation I get this condition. Okay, now let us take n cap along z axis. So if I take n cap along z axis, then the rotation vector will nothing but 1 minus epsilon 0 epsilon 1 0 0 0 1. Okay, now let us try to find out like special cases, what this condition entails in the special cases, like for example if I equal to 1. So if I equal to 1, then I will get Vx, basically I equal to 1 implies x, 2 is y and 3 is z. So Vx plus epsilon by IH bar, and here you have Vx commutation with jz, and that should be equal to R11 Vx plus R12 Vy plus R13 Vz. But here I have R11 is 1, R12 is minus epsilon, R13 is 0. So I will get Vx minus epsilon Vy. So I have Vx plus epsilon by IH bar, Vx commutation with jz equal to Vx minus epsilon Vy. And Vx gets cancelled, and from here I get Vx commutation with jz, epsilon will get cancelled, minus IH bar Vy. Okay. And similarly you can try it for I equal to 2, and there you will get Vy plus epsilon by IH bar Vy jz equal to epsilon Vx plus Vy plus 0. But again this Vy and Vy will get cancelled, and epsilon will get cancelled, and I will get Vy plus jz, Vy commutation jz equal to IH bar Vx. If you try I equal to 3, then you will get Vz plus epsilon by IH bar Vz commutation jz equal to, there is just one term, 0 plus Vz. But this Vz gets cancelled, and I have Vz commutation jz equal to 0. So let us look at our results. I have, for I equal to 1, I get Vx commutation jz equal to minus IH bar Vy. Vx commutation Jz equal to minus IH bar Vy. For I equal to 2, I get Vy commutation Jz equal to IH bar Vx. IH bar Vx. And for I equal to 3, I get Vz commutation Jz, commutation Jz equal to 0. Now if you look closely, you can find some kind of pattern, and basically I can write this as Vi commutation Jz equal to I epsilon IH bar k, I epsilon ijk. This is iota, and this is the this is index I, so these are different. ijk vk into h bar. So this is the defining condition for my vector operator in quantum mechanics. So a vector operator with components Vi, when commuted with angular momentum operator J, should give me I epsilon ijk h bar vk.